redshifted, right? Why are 4 of them not redshifted? Why are 4 not moving away from us? Yeah, well, they're moving toward us because maybe they're like orbiting us. I'm just guessing. Okay. Although Arizona, you can't see. You can see Andromeda. There's several of them just because of their chaotic motion are not moving away from us. Okay. Andromeda is probably one of them. Okay. So this is our first example here, and this is the formula that they have in the IB packet. This is the actual relativistic formula that's not in the packet. So if you're doing the problems from the textbook, some of them, this is a very approximate formula. Yeah? Okay? This is a more precise formula. So if the way we're doing it doesn't get the answer in the textbook, try the real one. Why they don't put this in the data packet? I don't know. Okay? Probably on the test you should use their crappy formula. Right? Notice that it is a change in wavelength formula. It doesn't tell you what the wavelength is. It just tells you how much it changes by. In all redshift problems, you're going to add to the wavelength. And in blue shift problems, if they're moving toward us, we're going to subtract from the wavelength. Right? So 486 nanometer line, that's the original wavelength. Right? So here we go. So that's the original wavelength. Right? Okay? Is approximately equal to the recession velocity divided by the speed of light, right? Okay, so a 486 nanometer line, that's its actual, right? That's its actual wavelength, right? Comes in at 495 nanometers. So what's our delta lambda? What's that? Is that 9 nanometers? Does that limit our sig figs? Yeah, it kind of does, right? We'll pretend maybe it doesn't, but right. So 9 over 486, we just lost a bunch of sig figs. We now have 1, really, right? Okay. And then that equals the recession velocity, which we don't know. Speed of light is 3e5 kilometers per second. Okay. Now, why am I doing kilometers per second and not meters per second? Because when we talk about these things, we always talk about recession velocities in kilometers per second. When we get to the Hubble law, we'll talk about kilometers per second of recession velocity for every megaparsec of, sorry, I was megaing before you came in. I wasn't, mega was not directed at you. 9 divided by 486 times 3e5. I'm getting the recession velocity to be 5.55, right? 10 to the third kilometers per second. Yeah. Was that in your little note guide? Was that the example? No? That's not there? That's sad. All right. What's on there?
Like change wavelength of 656.
No, okay, well, let's try that one. I think I've got that in there. Put that in your notes. Don't put that in your notes, right? What is the change in wavelength of a 656 nanometer line of a galaxy receding at 20,000 kilometers per second? What is the new wavelength? Okay, so let's go ahead and set that up. It's a 656 nanometer line. We're trying to find delta lambda, right? It's 20,000 kilometers per second divided by 3e5 kilometers per second. It's 3e8 meters per second, 3e5 kilometers per second. So 20 divided by 3e5 times 656. Okay, and I get that the shift is 43.7. Do you guys get that?
Yep.
Right? Now it's receding from us, right? It's moving away. It's going to be a red shift. Red wavelengths are longer than blue, correct? Right? So red shift means we add it on. So the new wavelength is going to be 656 plus 43.7, right? Okay, and you get 699.7 nanometers, or 700 nanometers. Yeah? Should we try the real formula? Why do we add? Because redshift is shift toward larger wavelengths. Red wavelengths are larger, right? They're stretching out. Remember the whole thing of Doppler effect, right? These things are stretching out as things move away from us, right? Say it again. Because that's the speed of light in kilometers per second. Yeah? So when you do recession stuff, you tend to work in kilometers per second. Don't forget to, if you need meters per second, the extra factor of 1,000, right? Let's try the fancy formula. What's the fancy one? The new wavelength is equal to the square root of 1 plus 20 E3, right? Divided by 5E5, divided by 1 minus 20E3 over 3E5, right? Speed of light, what's the speed of light? I don't know. It's approximately something, right? It's about equal to that. We're pretty loosey-goosey about the speed of light, aren't we? Oh, I forgot the original wavelength, 656, right? Okay, so 656 times the square root of numerator. So 1 plus divided by, okay, right parenthesis divided by denominator, 1 minus, I know, how do you do this? Like, you need like a bachelor's degree in like calculator to do this formula. Or a degree in computer science. I get 701. Right? So it's at least hopeful. 43.7 is a big change in that wavelength. Yeah? 43.7 divided by 656 is 6.6666. Did not pick that number by purpose. Okay, but anyway, that's 6% of the wavelength change, right? You can see that it's already not 100% accurate. And once you approach, 30%, 40% shift of the wavelength, better start using this. Hopefully they won't give us problems where you, right, have to use these approximate ones, but there it is. You have to do this, and when you do this, you have to do parentheses, and you have to also do parentheses, right, on your calculator. Like that. Are we good? Are we all exampled out on that one? You guys want to try some?
Now the IB test would make it bad if we use
the real formula?
Yeah.
No, they would definitely give you the benefit of the doubt.
Recording right now?
Yeah, I just turned off the wireless mic, though. That's the key. I hope it shuts off immediately.
5 minutes out of that one.
All right. Try that one. So now you're solving for V. Go ahead and use the approximate formula, because God forbid you'd have to solve for the V in this formula, right? There is a good side to the IB formula. There is a good side. Well, the thing that surprises me is that they give us that time dilation, gravitational time dilation formula.